Hi everyone, it's Janine here, and in today's video we are going to be learning about series solutions about ordinary points. So the goal is to solve second order linear differential equations with variable coefficients using series solutions. And so let's start off by introducing this theorem here, the existence of power series solutions to differential equations. So what this theorem tells us is that if x is equal to x naught is an ordinary point of the differential equation y double prime plus p of x y prime plus q of x y is equal to 0, then there exists two linearly independent solutions in the form of a power series centered at x naught. And a point x naught is an ordinary point if p of x and q of x are analytic at x naught. Otherwise, it is called a singular point. So let's go over the steps that we need to perform when solving a second order linear differential equation with variable coefficients using this method. So here's an overview of the steps that we need to perform when we are solving a differential equation using the method of series solutions about an ordinary point. So in step 1, we need to plug in our power series into our differential equation. And in this step, all we're doing is we are making the assumption that y is equal to the summation from n is equal to 0 to infinity of cn x to the n, and we're just applying the power rule to get our derivatives. And notice that every time we take the derivative, we need to up the index by 1. So for y prime, we have n is equal to 1, and for y double prime, we have n is equal to 2. And we're just applying the power rule here. So we're bringing down our exponent, so that's where this n comes from bringing this exponent down here. And we get this n minus 1 from subtracting 1 from the exponent on this x to the n term here. And same goes for the y double prime. We up the index by 1. And we bring down the exponent. So that's where this n minus 1 comes from. And we're also subtracting 1 from our power on our x term, so that's where this n minus 2 comes from. In step 2, we need to distribute our terms. In step 3, we need to set each exponent equal to k. In step 4, we need to match our indices. In step 5, we need to factor out x to the k. And in step 6, we need to determine our recurrence relation and solve for our cn's. And in step 7, we need to plug in the following two cases to get our two series solutions. So we have case 1 where c naught is equal to 1 and c1 is equal to 0. And we have case 2 where c naught is equal to 0 and c1 is equal to 1. And in step 8, we obtain our general solution, which is y is equal to c naught y1 plus c1 y2, where y1 and y2 are the series solutions that we obtained in step 7. And c naught and c1 are just arbitrary constants. So let's go ahead and take a look at an example and apply this. So in this example here, we have y double prime minus xy is equal to 0. And so as our first step, let's go ahead and assume that y is equal to the summation from n is equal to 0 to infinity of cn x to the n, and let's go ahead and use the power rule to get our corresponding derivatives. So we have y prime is equal to the summation from n equals 1 to infinity of n times cn times x to the n minus 1, and y double prime is equal to the summation from n is equal to 2 to infinity of n times n minus 1 times c n times x to the n minus 2. And now let's go ahead and plug this into our differential equation. So we have y double prime, which is equal to this thing here. So we have the summation from n is equal to 2 to infinity of n times n minus 1 times cn times x to the n minus 2. And then this is minus x times y, and y is equal to the summation here. So we have times the summation from n is equal to 0 to infinity of cn x to the n, and this is all equal to 0. And now let's go ahead and distribute this x into our summation here. So we end up with the summation from n is equal to 2 to infinity of n times n minus 1 times cn times x to the n minus 2 minus the summation from n is equal to 0 to infinity of cn x to the n plus 1, and this is equal to 0. And what we're going to do next is we are going to set our exponents equal to k. So for this summation here, the exponent on our x term is equal to n minus 2, so we're going to set k equal to n minus 2. And this is the same thing as n is equal to k plus 2. And then for this summation here, we have our exponent on our x term equal to n plus 1, so let's go ahead and set k equal to n plus 1. And this is the same thing as n is equal to k minus 1. And now let's go ahead and get our summations in terms of k. So for our first summation here, we have an n equals 2, so plugging this in to here, we have k is equal to 2 minus 2, which is equal to 0. So we have k equals 0 here to infinity. And then we have an n here, so let's go ahead and replace that with a k plus 2. And then we have an n minus 1, so let's go ahead and plug in a k plus 2 for n. And then we have minus 1. And then we have c, and then n, so n is equal to k plus 2. And then we have x to the n minus 2, so x to the n minus 2, so n minus 2 is just equal to k. And then for our next summation, we have n equals 0, so let's go ahead and get that in terms of k. So k is equal to 0 plus 1, so we have a k equals 1 here to infinity. So we have the summation from k equals 1 to infinity of c, and then we have our n, which we are going to replace with a k minus 1. And then we have an x, and then that is to the n plus 1. So we are going to replace this n plus 1 with a k. And let's go ahead and set this equal to 0. So we can see here that this summation starts off at k equals 0, and this summation starts off at k equals 1. So what we're going to need to do is take one term out of this summation here so that we can match our indices. So let's go ahead and plug in a k equals 0 here to get our k equals 0 term. So we have 2 times 1 times c2 x to the 0. And then what that does is that shifts our index up by 1. So now we have k equals 1 to infinity of k plus 2 times k plus 1 times ck plus 2 x to the k. And then this is minus the summation from k equals 1 to infinity of ck minus 1 x to the k. And this is all equal to 0. So simplifying this, we know that this is equal to 1. So let's go ahead and simplify this. So we have 2c2 plus the summation from k equals 1 to infinity of k plus 2 times k plus 1 times ck plus 2 x to the k, and then minus the summation from k equals 1 to infinity of ck minus 1 x to the k is equal to 0. So next, let's go ahead and factor out our x to the k. So we have 2c2 plus the summation from k equals 1 to infinity of k plus 2 times k plus 1 times ck plus 2 minus ck minus 1 x to the k, and this is equal to 0. And in our next step, what we're going to do is we are going to set our coefficients on the left-hand side equal to those on the right-hand side so that we can get our recurrence relation. So because there is no coefficient corresponding to x to the k on the right-hand side, it is safe to assume that our x to the k coefficient on the right-hand side is equal to 0. So let's go ahead and set our coefficients on the left-hand side equal to those on the right. So let's go ahead and start off with our constant term. So on the left-hand side, we have this 2c2, and on the right-hand side, we just have a 0. And on the left-hand side, we have this here. So this is the coefficient corresponding to x to the k. So let's go ahead and set this equal to the coefficient on the right-hand side, which is equal to 0. So we have 2c2 is equal to 0. And so from this, we know that c2 is equal to 0. And for the x to the k coefficient, we know that k plus 2 times k plus 1 times ck plus 2 minus ck minus 1 is equal to 0. So what we want to do here is solve for ck plus 2 because we want our higher coefficients in terms of our lower coefficients. So let's go ahead and solve for ck plus 2. So let's go ahead and add ck minus 1 to both sides. So we have k plus 2 times k plus 1 times ck plus 2 is equal to ck minus 1. And now let's go ahead and solve for ck plus 2. So let's go ahead and divide both sides by k plus 2 times k plus 1. So we get that ck plus 2 is equal to ck minus 1 over k plus 2 times k plus 1. So we have c2 is equal to 0, and this is our recurrence relation here. And this is valid for k greater than or equal to 1. So now that we have our recurrence relation, let's go ahead and solve for our cn's. So let's go ahead and start out with k equals 1. So for k equals 1, we have c sub 1 plus 2, which is equal to 3. And then we have c sub k minus 1, so k is equal to 1, so we have c naught over k plus 2, so 1 plus 2 is equal to 3, times 1 plus 1, which is equal to 2, so we have c naught over 6. And then for k equals 2, we have c4 is equal to c1 over 4 times 3, which is equal to c1 over 12. And then for k equals 3, we have c5 is equal to c2 over 5 times 4. So this is equal to c2 over 20. And we know that c2 is equal to 0, so this is just equal to 0. And then we have k equals 4. And so we have c6 is equal to c3 over 6 times 5. So we have c3 over 30. And we know that c3 is equal to c naught over 6. So let's go ahead and plug that in. So we have c naught over 6 times 1 over 30. So we have c naught over 180. So remember from earlier, we had made the assumption that y is equal to the summation from n equals 0 to infinity of c n x to the n. So we have c naught x to the 0 plus c1 x to the first plus c2 x to the second power plus c3 x to the third, and so forth. So now let's go ahead and plug in the coefficients we found into this assumption here. So we have y is equal to c naught x to the 0. So we don't know what c naught is equal to, so let's just leave it here. So we have c naught x to the 0, and then we have c1 x to the first power. So we also don't know what c1 is equal to, so let's just leave that in our answer. So we have c1 x to the first power, and then for c2, we do know what c2 is equal to, and it's equal to 0. So we have plus 0 x squared, and then we have plus c3. So c3 is equal to c naught over 6. So we have c naught over 6 x to the third power, and then plus c4. So c4 is equal to c1 over 12 x to the fourth. And then for c5, we have c5 equal to 0. So we have 0 x to the fifth. And then for c6, we have c naught over 180. So we have c naught over 180 x to the sixth. So now let's go ahead and plug in our two cases to get our two series solutions. So for case 1, we have c naught is equal to 1 and c1 is equal to 0. So let's go ahead and plug this in. So we have y is equal to 1 plus 0 times x plus 1 over 6 x cubed plus 0 over 12 x to the fourth plus 1 over 180 x to the sixth, and so forth. So this is equal to 0. This is also equal to 0. And so for y1 of x, we have 1 plus 1 over 6 x cubed plus 1 over 180 x to the sixth, and so forth. And so this is our first solution. And now let's go ahead and find our second series solution. So we have case 2. So c naught is equal to 0 and c1 is equal to 1. And so plugging this in to y, we have y is equal to c naught. So c naught is equal to 0. And we have plus c1 times x, and so c1 is equal to 1, so we have 1 times x. And then plus c naught, so c naught is equal to 0 over 6 x cubed. And we have plus c1 over 12, so we have 1 over 12 times x to the fourth power plus c naught, so c naught is equal to 0. We have 0 over 180 times x to the sixth, and so forth. So we have 0 term here. This is equal to 0. This is also equal to 0. So we have y2 of x is equal to x plus 1 over 12 x to the fourth, and so forth. So that is our second solution. So now we have our two series solutions, y1 of x and y2 of x, where y is equal to c naught y1 plus c1 y2 is the general solution to the differential equation. So that is how you solve a differential equation using the method of series solutions about an ordinary point. Thank you guys so much for watching. Don't forget to like, comment, and subscribe, and I'll see you guys next time. Bye.